Okay, another use of the divided difference table. Okay, so suppose I'm trying to model some data and I see something that looks kind of like that and I say, well, let's put another one in right there. And I say, well, gee, that kind of looks like quadratic data. And now let's say those really made a perfect quadratic. So, if this is 1, suppose I just had, let's make it really simple. Let's suppose I had x squared plus 1. Okay, so that if this is at 0, if that's 1, that's 2, that's 3, then the value here is 10, the value there is 5, the value here is 2, and the value there is 1. Well, so for those data points, so we've got 0, 1, 1, 2, 2, 5, and 3, 10. If I do a divided difference table, so set this up with my x, my y, my f, and I'm going to call this f1 just for short, and then I'll have an f2 out here, an f3. Okay, so we've got 0, 1, 2, 3, and 1, 2, 5, 10. Okay, so our first divided difference, 2 minus 1 over 1, so I get 1. Here I get 5 minus 2, 3 divided by 1, so I get 3. And here I get 10 minus 5, which is 5 divided by 1, so I get 5. So, I've got those. Now, for my second divided difference, well, I've got 3 minus 1 divided by 2 minus 0, or 1. And then I've got 5 minus 3 over 3 minus 1, which is also 1. And then, since those two values are both 1, it'll be very quick to see that if I go to a third divided difference, I get 0. Well, what this just told me here was that because f2 was the same for all of those, that told me the points lie on a quadratic. Okay, and the other, the 0 there, that also clues me in. But why this, that those are both 1? Well, because they're both the same. And remember, if you have, P equals A0 plus A1x plus A2x squared, that if I take P prime, well, I'll get A1 plus 2A2x. Okay, so that depends on x. So, well, these changed with different x's. But if I take P double prime, I get 2A2, a constant. Okay, so again, this is not the derivative, but it's akin to the derivative. It's a multiple of the derivative. And so those being a constant, that clues me in that I had a quadratic. If F3 had been the first place had been a constant, that would have clued me in that it was a cubic. If f1 was a constant, that would have said to me I had a linear situation. And so, in general, you probably aren't going to get an actual constant, but what you may have is something like, suppose this is f1, this is f2, this is f3, f4. What you may have, say, under f3 is you may get like a 2 and a 1.9 and a 2.1 and a 1.8 and a 2.05 and and that sort of thing. Well, as you look at those, they're all about 2. Okay, and I just chose 2. It could have been 1.35. They were all about 1.35. But they're all about the same number. This was an F3, so I'm guessing whatever all these points are here, these are a bunch of X and Y points, I'm thinking that a cubic would fit well. And if they are not close to the same value, I'm thinking a cubic won't fit very well. Okay, so we'll see that more with the next topic of least squares that we get to the next module. But this is a very nice use of divided differences, is to take all these points, look at the divided differences, and see if there is a column that appears to be relatively constant. And if so, then we can probably guess that degree of polynomial. So if it's f2, probably a quadratic. If it's f3, probably a cubic. That sort of thing would fit well. Okay, so there is another use of divided differences.